In the far South Pacific, there is a stretch of empty ocean that looks calm and unimportant. But beneath that quiet surface lies one of the most extreme places on the planet. Hidden under nearly 6 kilometers of darkness is the Pacific Antarctic Ridge, one of the most active volcanic zones on Earth, creating new seafloor every hour of every day. It is a volcanic ridge system where the planet is constantly pulling itself apart, releasing heat and magma on a scale no land volcano can match. Yet almost everything happening there remains unseen. That invisibility is what makes this place so unsettling. In the last 2 years, scientists have detected unusual clusters of earthquakes, mysterious chemical plumes drifting through the deep ocean, and signs that magma may be rising beneath several ridge segments. If these signals came from a volcano near a city, emergency alerts would follow. But out here, thousands of kilometers from any coastline, they unfold in total silence, with almost no monitoring to warn us if something changes. So what exactly is happening beneath this remote ocean? Could a disturbance here send shockwaves far beyond the deep Pacific? Let's find out. Don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. The Pacific Antarctic Ridge lies in one of the most remote regions on Earth. It forms the tectonic boundary between the Pacific Plate, the largest of all plates, and the Antarctic Plate. Running north to south through the deep Pacific, the ridge sits at depths of 4,000 to 6,000 meters, rising from the seafloor as a long volcanic spine built not by one volcano, but by hundreds of volcanic vents, fissures, seamounts, and magma chambers spread across its 6,000-kilometer length. Most of these volcanic centers have never been seen, mapped, or studied directly. Unlike slow-spreading ridges such as the Mid-Atlantic Ridge, which form deep rift valleys, the Pacific Antarctic Ridge spreads extremely quickly, about 60 to 75 millimeters per year. That rapid rate transforms the geology entirely. Instead of a deep canyon, the ridge crest is smoother and more elevated. Magma flows upward almost continuously to fill the gap created as the plates pull apart. Eruptions occur frequently, sometimes in small pulses, sometimes in long fissures, but always in ways hidden beneath kilometers of water. Because magma supply is abundant, hydrothermal vents thrive along the ridge axis. Seawater seeps into cracks, heats to extreme temperatures as it contacts magma chambers, then erupts back into the ocean as plumes loaded with dissolved metals. Transform faults, long fracture zones that offset ridge segments, link various parts of the ridge, and generate their own seismic activity. Over millions of years, this process has steadily built the Pacific Basin. As new crust forms at the ridge, older crust is pushed outward towards subduction zones around the Ring of Fire. In this way, the Pacific Antarctic Ridge acts as a tectonic engine that slowly expands the Pacific Plate and helps shape the geological dynamics of much of the planet. Despite its remoteness, the ridge hosts some of the most extraordinary ecosystems on Earth. In total darkness and crushing pressures, hydrothermal vents release chemical-rich fluids that sustain life through chemosynthesis rather than sunlight. Here, bacteria convert hydrogen sulfide and other chemicals into energy, forming the base of a food chain entirely independent of photosynthesis. Giant tube worms cluster around vents, absorbing nutrients through symbiotic bacteria. Clams adapted to darkness thrive near warm flows. Blind crustaceans crawl across mineral chimneys that tower several meters above the seafloor. These communities are isolated by vast distances and evolve independently, often producing species found nowhere else. Scientists first observed vents along parts of the ridge in the 1990s and early 2000s using remotely operated submersibles. They discovered black smokers, metallic chimneys, and expansive fields of microbial mats. But most of what we know comes from indirect evidence. Satellites detect small changes in sea surface height that hint at volcanic mountains below. Autonomous floats sample chemical anomalies that reveal drifting plumes. Dredged rocks show fresh basalt flows, proving eruptions occurred recently even when no one witnessed them. One of the ridge's most important scientific contributions is its role in preserving Earth's magnetic history. As molten rock cools, tiny magnetic minerals align with the current direction of Earth's magnetic field. Over millions of years, these patterns, known as magnetic stripes, are pushed outward by spreading. The Pacific Antarctic Ridge therefore records a long timeline of magnetic reversals, providing crucial information about the geodynamo that powers Earth's magnetic shield. The ridge also influences ocean chemistry. Mineral-rich vent fluids feed deep currents with essential nutrients, affecting ecosystems thousands of kilometers away. These currents flow into the Antarctic circumpolar current, contributing to global circulation patterns that regulate heat and carbon dioxide. In addition, by continuously generating new crust, the ridge helps control the long-term structure of the Pacific Basin, influencing how earthquakes and volcanism occur around the Pacific Rim. In short, the Pacific Antarctic Ridge is not just a geological feature. It is a biological refuge, a chemical engine, a magnetic archive, and a tectonic force shaping the world's largest ocean. Although remote, the ridge showed signs of renewed activity in 2024 and 2025. Seismic networks detected clusters of earthquakes along several segments, forming swarms that strongly suggest magma movement. Such swarms occur when magma forces its way upward, cracking the crust and opening new pathways. In late 2024, satellite data revealed thermal anomalies above one ridge segment. These anomalies, caused by slight changes in sea surface height, often indicate increased volcanic output. Around the same time, autonomous floats detected elevated helium-3 levels, a rare gas that originates deep in the mantle. Together, these signals pointed to a likely submarine eruption. In early 2025, researchers observed changes in the chemistry of one of the central hydrothermal vent fields. The vent began releasing hotter, more mineral-rich fluids, a shift that often occurs when fresh magma rises toward the seafloor and heats the circulating seawater from below. Several earthquakes added to the evidence. A magnitude 5.0 earthquake struck beneath a vent field in June 2025, followed by a magnitude 5.4 mid-ridge earthquake in August 2025, likely caused by a dike intrusion. In October, a magnitude 5.1 strike-slip earthquake shook a transform fault linking two ridge segments. More recently, another earthquake of magnitude 5.7 struck the ridge on November 13th. Individually, none of these events were unusual, but collectively, they portrayed a system undergoing significant changes, a ridge entering a more active eruptive cycle, with magma rising, vents shifting, and seismicity increasing. Although far from human populations, the Pacific Antarctic Ridge carries real risks. One of the most important is the potential for ridge flank collapses. Volcanic slopes formed by fast spreading can become unstable, and when they fail, the resulting underwater landslides can displace huge amounts of water. In extreme cases, these collapses could generate tsunami-like waves capable of traveling long distances across the Pacific Basin. Transform faults pose another threat. These fractures can accumulate stress and eventually release it in earthquakes that exceed magnitude 7. Such events can destabilize vent fields, trigger seafloor slumps, or shift large sections of the ridge abruptly. Hydrothermal explosions present additional hazards. When magma interacts explosively with seawater in enclosed spaces, the resulting steam blast can destroy vent systems and alter local ocean chemistry. Although the pressure at great depths suppresses the most violent types of explosions, they can still significantly reshape the seafloor. The possibility of tsunami generation cannot be completely dismissed. While subduction zones are the primary tsunami sources, large seafloor failures or fault ruptures along spreading ridges can produce waves that travel for thousands of kilometers. Yet the most significant danger is the lack of monitoring itself. The ridge has no permanent seismometers, no real-time vent sensors, and very limited satellite coverage due to its remote location. As a result, major geological events may occur without anyone noticing. The ridge represents one of Earth's most significant blind spots, an active, evolving volcanic system that few instruments watch. The Pacific-Antarctic Ridge will continue to spread and erupt for millions of years, and in the near future, scientists expect more eruptive pulses like the 2024 event. Magma is building beneath several parts of the ridge, and the hydrothermal systems above are already responding. As this activity increases, new vent fields may appear, potentially revealing entirely new ecosystems and species adapted to the extreme pressures and darkness of the deep ocean. Interest in the ridge is also rising for another reason: resources. Its hydrothermal deposits contain copper, zinc, and rare earth elements, making this remote region a target for future deep-sea mining, a prospect that raises major environmental concerns, especially in such fragile ecosystems. Over longer timescales, the ridge will continue pushing the Pacific Basin outward, influencing how and where subduction zones form, and redistributing tectonic forces across the Pacific Ring of Fire. These changes shape earthquakes and volcanic arcs from New Zealand to South America. Yet the greatest threat remains the unknown. With almost no monitoring, major eruptions, collapses, or large earthquakes could unfold without warning. It is a powerful geological engine operating in secrecy, a reminder of how much of Earth's activity happens beyond human sight.